The latest images captured by the James Webb Space Telescope have astonished scientists, providing insights into the universe that were previously unimaginable. Rather than simply expanding our comprehension of the cosmos, these images have revealed a puzzling reality, suggesting that our current understanding is insufficient to fully comprehend the early stages of the universe's existence. The established theories concerning the origins of the universe now seem to be stretching their limits, prompting the need to investigate alternative hypotheses about its formation. This raises the crucial question: how did the universe come into being, and why are these discoveries posing challenges even for the most experienced experts in the field of space science? It calls for a deeper investigation into the true nature of the Big Bang and its ever-evolving complexities. It may now be time to reconsider the Big Bang theory itself, as the public's perception of it has often been oversimplified. The Big Bang was not just an explosion within pre-existing space, rather it marked the very creation of space itself, unfolding approximately 13.8 billion years ago alongside matter and time. A core idea in modern science and cosmology is the concept of a singularity, a point where gravity becomes so intense that the curvature of spacetime becomes infinite. After billions of years since the universe's birth, we now realize that our cosmic home is part of a vast collaboration. For scientists, this discovery represents a vital aspect of the universe's existence, showcasing its ongoing expansion. The universe doesn't merely drift into existing space. Space itself is still expanding, contrary to traditional theories that suggested otherwise. It is believed that the first stars began to shine roughly 200 to 300 million years after the Big Bang, marking the end of the so-called dark age of the universe, when the first bright celestial objects formed and evolved into galaxies. However, the speed at which these galaxies developed remains a mystery. A major breakthrough occurred on July 22 when the James Webb Space Telescope released its first images, revealing several galaxies, some of which were already in existence about 300 million years after the universe's creation. While younger than the galaxies we see today, these early galaxies were smaller and less massive, in line with the scientific models at the time. In the early universe, the matter density was too low to form galaxies as large as those we observe in the present era. This discovery began with the detection of 6 notable redshifted bright spots by the James Webb Telescope, igniting one of the most significant cosmic puzzles in recent years. These newly discovered galaxies, though comparable in age to previously identified galaxies, appeared almost as large as our Milky Way. This finding has intrigued researchers in the field of Big Bang cosmology. When scientists analyzed a series of images taken by the telescope's near-infrared camera, they confirmed the existence of these distant objects. They used redshift data to determine that the light from these galaxies had traveled over 1 billion years before reaching Earth. This suggests that these galaxies existed between 570 and 700 million years after the confirmed Big Bang. This remarkable discovery challenges traditional cosmological expectations, which had predicted the formation of much smaller, less evolved galaxies at this stage of the universe's history. Instead, the James Webb Space Telescope revealed galaxies nearly as large as the Milky Way, defying these predictions. The gravitationally bound stars in these galaxies had already accumulated mass surpassing 10 billion times that of the Sun. One of these galaxies even seemed to possess a mass greater than 10 billion solar masses. However, whether this hypothesis is entirely accurate is still open to debate. Even if these findings are correct, the mass in the early universe would be far greater than anticipated, creating an even more complex puzzle. The discovery of these galaxies poses a significant challenge to nearly all traditional cosmological theories. Even if just one of these galaxies proves to be accurate, it would force us to re-examine our assumptions about the existence of these early cosmic structures. The matter density in the early universe would need to be far greater than initially assumed. Another potential explanation is that these galaxies may have formed in ways entirely unknown to us. These discoveries have raised questions that demand a reassessment of the Big Bang theory. Many space scientists are frustrated by these revelations, and their concerns are frequently expressed in scientific publications. Those who challenge the prevailing theories are often labeled as unorthodox or extreme. However, it is evident that even those who continue to support the Big Bang theory face unresolved questions. Among these is the fundamental issue of how 13.8 billion years ago something could emerge from nothing. Could something truly come from nothing, or was there a catalyst for this event? Did it occur randomly? Stephen Hawking famously pointed out that the nature of time as we understand it began with the Big Bang. Similar doubts arise concerning the uniformity of radiation and matter throughout the universe. Regardless of where we look or at what distance we observe, we see a similar distribution of systems, nebulae, and radiation across the cosmos. Modern scholars explain this phenomenon with the theory of cosmic inflation. However, other experts have expanded on this theory, suggesting that the universe expanded in a turbulent manner. According to this model, expansion occurred only in localized regions like bubbles, while other areas continued to expand without end. This model raises the intriguing possibility that other universes may exist within these expanding bubbles, each governed by its own set of physical laws. Such a perspective implies that our universe may not represent the totality of existence, but rather be part of a larger and more intricate structure. However, this is just one of many theories in cosmology. For instance, an article published in NASA's Big Time magazine in 1955 suggested that the universe may have never had a Big Bang and could have always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would be absent, with the continuous evolution of matter giving the impression of gradual development over time. One particularly captivating hypothesis arises from quantum physics and string theory. Some experiments have hinted that our entire universe could be a projection or simulation from a higher dimensional reality. While this might sound like the premise of a science fiction story, it connects to the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization capable of utilizing the energy of a galaxy might be able to create an ideal simulation of a universe. Exploring the depths of cosmology and the origins of the universe brings us into a realm of great mystery and ongoing scientific investigation. The new images from the James Webb Space Telescope have reignited debates about the very fabric of existence, putting established theories to the test and urging scientists to reassess core principles of our understanding of the cosmos. This idea, known as timeless inflation, envisions the cosmos not as a singular event or linear timeline, but as an eternal dynamic tapestry of universes constantly birthing and evolving within an infinite multiversal framework. In this context, what we perceive as the Big Bang may simply be a local event, just one of many cosmic awakenings occurring across an unimaginable expanse of time and dimension. This perspective reframes our place in the universe. Instead of existing within the universe, we might inhabit a universe, one among countless others. Each of these could be governed by distinct physical laws, particles, and dimensions, potentially rendering our understanding of physics as local, not universal. Such a possibility reshapes cosmology into not just a study of our universe's past, but a quest to understand a broader cosmic ecology. This broader view also revives ancient philosophical questions. What is the origin of existence? Can something truly come from nothing? Are the laws of physics themselves emergent properties of deeper principles? We have yet to grasp these questions, once purely metaphysical, are increasingly becoming relevant in scientific discourse. For example, some string theory models suggest that brain collisions in higher dimensional space could trigger Big Bang-like events. In these scenarios, two vast membranes or brains could collide in a higher dimensional space, releasing enormous energy and giving birth to a universe like ours. If true, this would imply our universe has a cyclical origin, not from nothing but from prior cosmic structures we cannot currently detect. Other models lean on quantum gravity or loop quantum cosmology, which propose that the universe did not begin from a true singularity but rather bounced from a prior contraction phase. In this model, the Big Bang is not the beginning but a transition, a cosmic heartbeat between collapse and rebirth. The James Webb Space Telescope's data may provide indirect evidence for or against such models, depending on what it reveals about the universe's earliest structure. Yet, all of this leads to a profound realization: our current models, no matter how elegant, are incomplete. The James Webb Space Telescope has opened a new window into the past, but the view it offers is both awe-inspiring and deeply unsettling. It shows us galaxies forming sooner, growing larger, and evolving faster than predicted. It shows us cosmic order where we expected primordial chaos. And in doing so, it forces us to confront a fundamental truth: science thrives not in certainty, but in the humility to question. As researchers continue to decode the telescope's findings, the scientific community stands at a crossroads. Should we revise existing theories like inflation, dark matter distributions, and structure formation, or are we on the cusp of a paradigm shift, one where entirely new frameworks must be constructed from scratch? Either way, one thing is clear: the universe is far more intricate, dynamic, and mysterious than we ever imagined. And in this growing web of galaxies, equations, and cosmic riddles, humanity finds itself not with answers, but with better questions, perhaps the most valuable discovery of all.